Okay, put your laptop down. This is just for the recording. This isn't for like a PA or anything.
Okay.
Just put that in your pocket.
Thanks.
You're good to go.
All right.
Thank you.
Thanks. Cool. And it's the stick to point, is that right?
Yeah, that's
Okay.
this thing.
Ah, okay.
Do you want the clicker of it?
No, no, no. Thanks. Yeah. Let me see. This works. Okay. That's okay. I might, but I should be fine with just one. So. Yeah. We can start. Yeah, it's fine.
All right, let's continue. After overrunning this morning, I'll now get out the whip and strictly enforce 15 minutes talks maximum. I will get some chocolate for people that run shorter than that. So again, the idea of this thing is being interactive. Try to keep in terms of information that you give, less is more. In terms of discussion that you spark, more is more. So let's try to get back to the style that we had this morning with David's talk and spark discussion and maybe reduce the number of slides a little bit. All right, so now we're happy to have Ravi kick us off with information.
Okay, so thanks. So it says overview, and so that means I'm going to try to just touch on overview points, and some of the details will get fleshed out in Vincent's talk and Marcello's talk and so on later in the session. Yeah? And so I may even be able to win some of the chocolate, I think. We'll see. So first is just to make the point that a lot of this is motivated from trying to interpret measurements of galaxy clustering in the language of the halo model. And so what we're usually doing is we're taking the observed signal and then we split it up into, if it's a 2-point correlation function, into pairs, and we either say the pairs are in the same halo or they're in separate halos. And then we might break the pairs that are in the same halo up into the center satellite pairs and the satellite-satellite pairs. And these were the things that Booth was a little bit worried about, whether in his lensing measurement he needs to distinguish between these, and experts do this split. Yeah. Though, so you should think of this as the number of pairs is the center satellite pairs plus the satellite-satellite pairs, and that's correct. So if you say it that way, yeah. And I think that's a useful way to think about this, because at least when I have incoming grad students and they see the halo model for the first time, then they start to wonder, you know, we typically write it this way, and this way, okay? And then this guy we use linear theory for, okay? And then the question is, we write one halo, but what we really mean is the convolution of two density profiles. And so it's not a psi, it is a 1 plus psi when we write the one halo term. Yeah.
I still have a problem with that.
Okay.
Because if you have n in front of it, then in both terms you will not have the same n.
Ah, good, okay. So, all right, okay, fine. Okay, yes. Yeah, so you're saying this should be n center satellite and this should be n satellite. Very good, thank you. Yes, good, okay. All right. So we typically write them as integrals over halo mass, where we would say, you know, the number of small-scale pairs is the dark matter pairs, and then we weight the dark matter pairs. This is the number of n minus 1, so second factorial moment of discrete counts, and we integrate over all halo masses. Yeah? So that's the way we do this. And when David was talking, he made this comment that, you know, the way the halo model works is you typically just say that this depends on halo mass, but there's no particular reason why you can't treat this guy as a vector of all the variables that might matter for halo formation. And so when David put his slide up and he had luminosity was some function of halo mass and formation time and all that stuff just sits in this vector here, and nothing else changes in the formulation. Yeah. So because you're doing pair counts, then you would care about the number of pairs in a halo, and they have to be distinct pairs, so that will be n minus 1, and then you average over all of those at fixed halo mass. So that is G2. If you were doing, you do the third factorial moment and so on for the higher order moments. Okay.
But that could also be dependent on the psi of matter.
What?
When you look at it as a vector, the concentration could be correlated with the number of galaxies and all this stuff.
So I'm imagining that this guy is a vector, and I have some number. So my halo will have many different types. That you're saying something else?
No, I'm saying that that number could also depend upon the psi, dark matter, and
The number of dark matter particles or whatever.
no, this is like the concentration, right?
This is, yeah. In here you would put halo concentration. So this is the halo profile.
So numbers could depend upon the concentration.
That's correct. So the number depends on all properties of the halo: mass, concentration, formation, redshift, blah blah blah. Right? So whatever property of the halo sits here. You're saying more than that?
No, well, I mean, psi, dark matter, and you know, there is another integral over the concentration. Right?
No. So you should imagine that here. Okay. So here you have lots of integrals, right, for each of them. No, because if you write this guy as a vector, then this is a vector, and so you have to integrate over. M is a vector. Okay. Yeah. And so in principle, you don't have to change anything. The problem is to know what that vector is, right? What the important elements of that vector is, and that's the point David was making earlier, is that we know mass is the important guy, and then what else do you add to that? Okay. All right. So I guess so I've said that. Problem is to identify the elements of the vector. Okay. So now we have a question, right? Because we don't know the elements of that vector, and so I'll again touch on a point that David made. So one option is to parameterize. So you write down all possible things that are allowed by symmetry. And then you leave them as free parameters and you marginalize over them. That's one option. And the other is to say, no, I'm going to try and study this problem. And so I'll try to reduce the ignorance rather than parameterize the ignorance. And we'll try to figure out which subset of parameters is important. Okay. And so so far, that's the approach I've taken. More than this, though it turns out that once you start taking this approach and you use the peaks model, all the terms that show up here are already built into this kind of structure. And so, so far, we haven't missed anything that shows up in the more general parameterization. Okay. Then the way this approach works is you formulate everything in the initial conditions, and then you try to propagate forward. And this is not an obviously right thing to do, but that's the approach, right? And so the first step is specifying everything in Lagrangian space, and then the next step is the evolution. Okay. So I'll talk first about that first step, which is specifying things in the initial conditions, and then a little bit about the evolution. So the recent progress comes from work of Marcello here, Asim, who's not here, Paranjpe, Vincent Dejac, where this was merging peaks theory, which is an old theory from the 80s, with the excursion set approach, which is an old theory from the 90s, with so a lot of the work was just merging these two things. And then the final thing is that since the time that these guys were working, we know that we have to care about more than spherical collapse. And if you add other variables than the density, which is the only one that matters for spherical collapse, then you have what in this language is called the stochastic barrier, and that's stuff that Ho-Jun has worked on as well. Yeah. Okay. And so the basic idea is that the number of halos, the number of peaks, the number of biased objects of mass m is some integral over the initial conditions, which is a Gaussian distribution with lots of different parameters. Typically, so the simplest models had, you wanted that the density was dense enough at the initial time so that an object could have pulled itself together to form by the present time. But in principle, it could be more complicated than that. It could be that the object had to be separate from other objects so that when the object pulls itself to form a halo today, it's not embedded, it's in something that is larger. And so the excursion set approach was designed to solve that problem, but it didn't quite. And the peaks problem solves that much better because it says you have to identify a peak. And if you've identified a peak, then you are by definition separate from nearby things. And so to define a peak, you need to say that the first derivative of the density is 0. The second derivative has the right sign so that you're a peak. And so you care about derivatives of the density. And so you could imagine playing the game and going further down this route. Then you can say, well, is it obvious that spherical collapse is the right answer? No, more things may matter. The shear field may matter, so you put the shear field here, and so on. So there's a bunch of variables that come in here. And for every variable that you put here, you will end up getting a bias factor. And the bias factor is some description about how differently clustered these biased objects are from the underlying dark matter field. And they should be differently clustered because you're going to be specifying that delta should be above some threshold. You're going to specify that this first derivative must take a special value. You're specifying, so you're specifying lots of special values. And so you're not picking random positions in the field. And sort of the nicest or the most intuitive way for me to think about what the bias factors are really talking about is to say, what if I wanted to calculate the large-scale density field, given that I'm centered on a halo? So this is the cross-correlation between halos, peaks, and the mass distribution. And so that's just some conditional distribution, right? Given that you're sitting on a halo, so sitting on a halo is this big guy here, and you want the large-scale density given all the constraints. Yeah? And then you just do this integral. I hope that's making us colder, right? So this shows clearly that, you know, this density profile, given that you're centered on a halo, is going to depend on all the constraints that you put. And so every little guy that sits here shows up, and we call that bias. Yeah? So if you want, how different this density profile is from the correlation function of dark matter is what bias is talking about. Okay? And that bias depends on lots of different things. There's a term that I'll come, which has been interesting in the last few years, which is this thing called velocity bias. And that is because, so derivatives of density, this guy will correlate with this guy, but this guy won't correlate with either of these two. A derivative of density will correlate with a first derivative of potential, and first derivative of potential is a velocity. And so if you're putting a constraint on this guy, you're putting a constraint on the velocities of the bias tracers. And because people were interested in using redshift space distortions to constrain cosmology, people care about this kind of velocity bias. Yeah? So it comes really from that term. Yeah. We're going to come to the evolution. Yeah. So I'm setting up sort of one theme of this is we've set up a fairly complicated picture in Lagrangian space with lots of effects, and in the data, currently people fit linear scale independent bias, and that works pretty well. And it's not an obvious thing from this setup. Yeah, and so it depends what error about. Yeah, that's fine, right? So we're trying to look forward, but it's also true. You would also like to know in an approach like this, which has all these bells and whistles, how come things end up being relatively easy in the data when you have big error bar? Okay. So to illustrate how this works, I'm plotting on the x-axis distance, and for now I'm scaling all distances by the size, by a characteristic size. So let's pretend I'm looking at objects of a certain mass. Okay, and when we look at those objects of a certain mass, then we have a choice as to how we want to define these objects. So one way to define these objects is just to say it should be dense enough, and on a larger scale it should be less dense. Okay, and that's the usual excursion set approach. And so if you do that, you look around, you say, I'm going to look in my initial Gaussian field, and I'm going to identify all places that are denser than a critical threshold, which is given by physics, so something to do with spherical collapse. And the density profile is lower on a larger scale. So the only constraint was on density and density on the next larger scale. Then let's look at this pink curve. You will predict a profile that looks like this. Okay, and the value, you know, how different the slope of this guy is, or you can take the ratio of this guy to the dark matter correlation function on these large scales, and you would call that bias. Okay. Then if you say, well, you know, I don't think that this was enough of a constraint. I would really like to be sure that I'm isolated, so I will require that I am a peak. So if I require that I'm a peak, then I go to BBKS, and the density profile that you predict by adding the constraint that you're a peak is steeper. And it's steeper because you've added the constraint that next to you there was nothing. You were a local maximum. And then if you say, well, I want to have put both constraints. I want both to be a peak, and so a peak in spatial position, I'm a maximum, and in spatial scale, I'm maximum. Then you get even steeper. Okay, so you go from this up to this up to this. So adding the peak constraint to the excursion set approach is a big deal. Adding the excursion set approach to the peaks is not such a big deal. Okay, and then we can play this game for large smoothing scales, which translates to high mass halos, or to small smoothing scales, which translates to low mass halos. Okay, and peaks are automatically upcrossing, but not. So they're upcrossing. So they're upcrossing in a strange sense. No, a peak is to define a peak, you fix a smoothing scale, And then what you did is you made a statement about if you offset from the position. You didn't make a statement about if you sat at the same position but changed the smoothing scale. The two are correlated, which is why the difference is there, but it's small. Not for Gaussian. For Gaussian smoothing, they're exactly the same, but in general, they're not. For this one is Gaussian for one of these guys, but not for the other. So that there's okay.
But a simple constraint about being upcrossing doesn't, it's not enough to ensure that the small peak is not in a...
Exactly, it's not enough.
Okay,
Yeah, yeah.
so that's still coming.
That's right. So you've got to put the peak. So that's what I'm calling excursion set peaks. You've got to add the upcrossing to the peak constraint. Sorry, you've got to add the peak to the upcrossing constraint. Yeah. Yeah.
I guess I'm missing something. So it looks like the smaller peaks, the low mass peaks, have a higher bias here.
Okay. So it looks like it's a. Okay. So let's look carefully. So So these are low mass halos. Low mass halos means that this RP is actually a smaller number for the low mass halos. But if you see that on small scales they are high, so on scales smaller than that on which you defined the peak. But as you go to larger scales, this drops and the bias is below. So the signal is below the profile associated with higher mass halos. Yeah, and so yeah, so this side is inside and this side is outside. So the curves are all crossing on the same scale because we said they should be delta C. Okay, and so there's an important lesson here, which is that generically in these models, the low mass guys will have steeper profiles. So it happens that that's true for the late time profiles, the NFW concentration. The low mass guys are more centrally concentrated. You get it for free here, but it's not obvious that this is the only thing that makes that trend. Okay. Okay. The other thing to notice is that generically, steeper means that you will fall more, and that means that in these kinds of models, high concentration means low bias, and so you're going to get assembly bias from this kind of thing. Yeah? And you should imagine that in practice, what I'm showing you is the mean profile given the constraint. There's some scatter around that mean. And so at fixed halo mass, there will be a range of these kinds of profiles. And so there will be around this, for low mass halos, there will be some scatter, and the guys that scatter up will tend to scatter down. Yeah. Okay. So that's sort of setting up some of the assembly bias stuff that Marcello might talk about. So the bias depends, so it's not just a number, okay, because you can see that if I divide this guy by this guy, I'm going to get something that's scale dependent. And so if I divide each of them by the dark matter, then they're not both scale independent ratios compared to the dark matter. So in general, the bias is K dependent, or is scale dependent. Yeah. This is the halo. This is the scale on which you define the halo. So think of this as a megaparsec. This is inside a megaparsec, and this is 100 megaparsecs. Yeah. So this is where linear bias should work. This is where the bias becomes K dependent, and then there's whatever it is inside. But all this is Lagrangian, so it evolves. Very good. I agree. Yeah. So correct. Yeah. So yeah, that's right. So the maybe I should show the picture. Okay. So right. So the bias will now be. So I was showing you that thing in real space. I had a setup thing to show you a similar measurement in Fourier space. Right. So again, you're measuring the cross correlation between halos and the matter. And then you take that measurement and you divide by the power spectrum of the matter. And so the fact that this is a constant at small scales, at small k is the usual linear bias, and then it's scale dependent as you go to larger k. Yeah? And there's a variety of things that make this scale dependence. This one is for low mass halos, and this is for high mass halos at different redshifts. Okay, so it's always, once you start getting to reasonably small scales, reasonably large k, the bias can be quite, or this ratio can be quite k dependent. And then the question is, how do we describe that k dependence? And the way we describe that k dependence is to say, well, bias is a function of k. There's a constant term. And then you start getting other terms. And like I said before, everything that you use to define a halo, like it should be a peak, not only should it be a peak, you should be upcrossing. Each one of those constraints comes with its bias factor. Okay? And so one of the pains in this game is that, so here this is constant bias. This one is coming from the peaks constraint. This one is coming from that if you change the smoothing filter, you should still be above the critical density. And so it was how you change the smoothing filter that made a difference. So each one of these guys comes with its new k dependence. So the bias factor is not k dependent, but it is multiplying something that depends on k. And generically, that first term is a k squared. Okay. All right. So these coefficients, they will depend on halo mass. And then how many you have depend on what it takes to define a halo, which we don't know a priori. Yeah. Okay. One of the things that is clear is that if you look at the measurements, then there's some k dependence, because it's clearly not a constant, but it goes up and it falls down, and it falls down, and it goes negative, and it can oscillate. And so that means that the bias, this one might have given you a k squared. This is just a number. This guy potentially gives you wiggles, gives you oscillations, depending on the shape of W. If W were sharp in k space, then you wouldn't get the oscillations. If it was sharp in real space, you will get oscillations. If it were Gaussian, you wouldn't get oscillations. And so the fact that we see oscillations is telling you that something like a top hat in real space must be right. What is the... So in this case, the halos were found with some friends of friends, or this one was spherical over density. That's sharp boundary. But that's right. It's by definition. Okay? Yeah. That's right. These are traced back. So these were, the measurement is little, doesn't really have a top hat built into it. Okay? You identify the halos so that they're a finite set of particles. You trace them back to the initial conditions. It's still a finite patch of some size. Okay? But you're not, I mean, but this measurement is, you sit on a point, and now you just measure all the particles, all the mass. So there's no boundary that comes in. Yeah. Yeah. What's that? No, that's not true. They're all here. This is the cross correlation between the halo and all the matter. No, a halo is a position, and you just count all the dark matter particles around that position, whether or not they are halo particles. It's a usual cross correlation, right? Yeah. This is cross correlation. It's not the auto. This is the halo matter. Well, we can talk after, yeah? Halo position mass, yeah. Right. So in real space, this part was all inside. And so here you could say, if I saw some sharp thing, that's by definition, because you found it with a sharp edge. But there's no real feature. So, but anyway, so one takeaway is, so you have a bunch of these numbers, right? And one of our problems is that when we fit to data, how many of these numbers do we want to allow, right? And worse than that, this was just linear bias. Then when you go to second order bias, again, you have a bunch of k-dependent terms. And so you have a bunch of free parameters. And so you're ending up with, if you just allowed yourself lots of terms from lots of symmetries, you have a ton of potential bias factors, and you don't know what to do. Yeah. Yeah. So for peaks, it stops here. It comes just with k squared, and that's just an analytic thing because you put a constraint on the gradient. Yeah? And then if you add to the peaks, you add the excursion set thing, you get this extra term. But okay, and this guy has lots of higher order k's, right? There's a k squared, but there will be k4 and so on. Okay. And so one of the issues is, in principle, there are a bunch of these terms. And so how many do you have to hang on to? Okay. So initially we thought, we're helped a little bit because it turns out that there are consistency relations between these coefficients. So if you added up all the bias coefficients, then you get, if you're doing linear order, so linear bias, there might have been a bunch of these guys, but if you add them all up, they give you a simple term, okay? And to the guys who are old enough to remember BBKS, this is the formula that Kaiser used for bias, okay? So if you want, this thing is just saying, if my only constraint were on the density, objects have to be height delta C, then that's the value. And so the consistency relation is all these bias factors. When you sum them all up, you get that one number, because the only constraint was on the density. When you go to second order, then B2, you sum up all the bias factors, and the sum of those two is, again, just some simple function of these guys. For the aficionados, it's the Hermite polynomial of second order, and so on. So you can write out what should be that thing. So this kind of helps, because you're reducing the number of free parameters, but it doesn't help that much, right? Because you just have the one consistency relation. You can turn this around, and there are a few other ways to cast the consistency relation in terms of, I can think of this as the typical profile around dark matter. I can think of this as the typical profile around dark matter because, so if I write down in a Gaussian field, what's the probability of being height delta C? What's the mean profile around a patch of height delta C? Then you end up getting this expression. You can ask, what is the mean curvature around a patch of height delta C? And so then there will be a consistency relation involving just this guy, where we wanted to talk about mean curvatures. There will be a consistency relation associated with doing all the mean upcrossings. Okay, so there are a bunch of consistency relations that you can use to reduce the number of free parameters. But to do that, you then had to know what was the value, the critical density for collapse. And a priori, we don't know that. Yeah? So while there are relations between the guys, we don't know what this number ought to be. We sort of know it should be of order unity, but we don't really know what it is. Worse, we know that in principle, the collapse is, or what makes a halo is not only its density, but something about the shear field might matter. Something about its shape might matter. And so all that stuff, like I said in the beginning, gets called stochasticity in the barrier and the critical density. And so it turns out that these consistency relations survive that, okay? So when you go through and you work out and you say the critical barrier to be crossed is not just one number, but that number can fluctuate. There will be an average, and you just plug in that average value here. Okay. So then you have to think a little bit about what happens when you do second order bias, because then you will have B2, and so, you know, do you put delta squared or do you put the mean of delta squared? But that's technical stuff, and that's okay. It's under control. You can use these consistency relations even when there's stochastic bias. Then you might wonder, well, you know, you're going to, we're also interested in assembly bias. So what's assembly bias in this language? So assembly bias in this language is to say, you know, in principle, bias depends on, you know, there are all these k-dependent pieces, and these numbers that sit here, they depend not just on halo mass, but they also depend on the steepness of the profile, how isolated it is. So they depend on all the parameters that you use to define a profile. And so if you, the common approach is to say, you know, only halo mass matters, which means you've integrated out all the other parameter dependencies. So you're presenting an average value of B10, an average value of B01, and so on. And those are the values that people usually report, okay? Because they just paid attention to halo mass, not halo mass and steepness of profile. But because this consistency relation works at the level, you know, before you've done this averaging, okay? So the consistency relation is a more fundamental thing. It survives assembly bias. If assembly bias is defined as saying these numbers depend on more than just halo mass. Yeah? So if these numbers depend on the smoothing scale, which gives you the halo mass, as well as steepness of profile and so on. So these numbers have assembly bias built in. This kind of consistency relation survives that. So that at least is useful. You don't have to worry about that for using it. But of course, like I said, what we don't know is what is delta C? What is this critical density? We have models for that. We can try to calibrate that in simulations, check if they work. Cristiano's done a bunch of work with this as well. But that's a gap, right? That's where some work needs to be done. Just to check that this makes sense, we've tried to turn this around, and we've tried to say, from the large-scale clustering, I can measure these numbers. The sum is supposed to give me the critical density. And now I can go to the simulations, and I can actually measure the density of a patch in the simulations and see if indeed the sum of the large-scale bias gave me the small-scale density. Yeah, so it's kind of a non-trivial test. And so here's the sort of thing. We measure bias as a function of halo mass. And the yellow curve is showing you what the bias would have been if we were doing only spherical collapse. And the blue band is saying we think that something like the shear also matters. Okay? So this is sort of the prediction, the usual prediction that you would see from a peaks theory-related model. These are SO halos, I think. And then we can measure this term is the one that's giving you the k squared of the bias. We can try, and so we measure that from the data. This is what Peake's theory would have said it should be. Okay. So it doesn't quite work, but we can then do the sum, right? We can sum B10 with B01, and that should give us the delta C. Yes. So in principle, so what we've done here is we've done a marginalization so that I'm only showing you 2, but you're right. In principle, we could do this more carefully with 3. But we're just doing this to see, just a second, I'll come back to this, if we get this okay. Yeah. Now it looks like this band is pretty big, but look where it's really a 10% band, right? Because we're going from 2 to 2.2. Yeah. So this is a sort of non-trivial statement, right? Because it's large-scale bias that has predicted. We've taken the sum of the bias factors to get the critical value of the density of the patch, and that patch is a very small thing. So these were measurements that were made on 50 megaparsec scales, and the patch is a 1 or 2 megaparsec thing. Yeah? And so this at least seems to hang together, not yet at 1% precision, okay? But the approach seems okay. A last slide about evolution. So that's all doing stuff in the initial conditions. What we would like is to know in the evolved field, what does the bias look like, because that's what we actually observe. And the two are related typically by this factor is just a 1 with no k dependence. If peaks is the right picture, then this number here comes with k dependence, and that thing is called velocity bias. And the velocity bias, if you write it, works in this way. So the result is that the Lagrangian bias, you add what would be a 1 at the present time. In general, you add the growth factor. From the k squared, the k-dependent piece, you subtract the growth factor. And so one thing to notice is that because you added the growth and you subtracted the growth, if I do the consistency relation, this sum would have been the Eulerian, and the Eulerian, the sum of the two Eulerians is the same as the sum of the two Lagrangians. So the consistency relation survives when you go to Eulerian. Okay. The other thing to notice is that for this kind of model, as time goes on, the growth factor is becoming bigger. And so this bias factor is becoming, if it were positive, this bias factor is being reduced. And so the k dependence is being reduced as the system evolves. And so that's one reason why when you make measurements in Eulerian space, the k dependence is less of an issue. Yeah? It's going away in this kind of model. Okay. There were measurements by Tobias last year and Vincent and Urosh looking for this velocity bias. And so here they're looking at the same halos, and they're measuring the halos at different times. They're doing the cross correlation between the halos and the mass at an early time and a late time. And so you're supposed to see that the bias went from being a small number to +1 at the present time, bias +1. So that's the evolution. The lines through the measurements are the k-dependent bias that is evolving because of this sort of thing. And that works better than not including. So the dashed line is if you did not include that k-dependence. I guess Tobias will show, I'm not sure, some of this. No. Okay. They have another method of showing this, but I won't talk about this. Yeah? And so again, the important thing is even in the evolved field, because of this velocity bias, the consistency relations are preserved. Okay. I guess I'm short on time, so I should stop there. I had a bit more about voids and how this works for voids, but you can talk to me later about that. Yeah. Okay, thanks.
So in your plot, there's that blue band
Yeah.
you're showing. So is that just the Doroskovich spread of ellipticities, or is that something else?
It's a little more, it's the Doroshkevich spread of ellipticities, but around peaks. And so Doroshkevich's formula would be for all positions. And so you can do that calculation around peaks, and that's the kind of spread.
For halos, it's possible to measure the actual density at the peak of that halo.
Yeah.
Right.
So that's what the dots were rather than the band.
Oh, okay.
So there were.
Okay,
So we were doing a comparison where we actually measured the density versus predicting it from the bias.